I'm so excited to explain chemical equilibrium to you in this video. So the first thing we'll talk about is what equilibrium actually is in relationship to a chemical reaction. Then we will discuss how you write an equilibrium expression from a balanced chemical equation. And then finally we will talk about what is Keq and what is Q, and how do you calculate them and what do they mean? All right, so let's discuss what chemical equilibrium is. Before we do that, though, let's talk about how chemical reactions work. So in this class, we've been talking about chemical reactions as if, your reactants combine to form your products, and then the reaction stops. So once you run out of one of your reactants, the reaction just ends, and then, you're done. Those kinds of reactions do exist. So for example, when you burn methane in the presence of oxygen, that reaction is finite. It goes only in one direction, produces carbon dioxide and water, and then it will stop. And you don't find a reverse reaction, meaning that carbon dioxide and water don't spontaneously combine and reform oxygen and methane. So you can't unburn something. That kind of reaction goes only in one direction. Your reactants become your products, and then the reaction stops. This is called an irreversible reaction. But in the real world, you will find that there are plenty of chemical reactions that actually don't just go in one direction. So an example of that would be this reaction with sulfur dioxide and oxygen. If I were to take sulfur dioxide and oxygen and put it together in a container and close the container so that it couldn't escape, you would find that they would combine to form SO3 molecules. And as soon as you start forming SO3 molecules, those SO3 molecules would decompose back into 2 sulfur dioxide and 1 oxygen molecule. And then, of course, those would combine and form our SO3, and our SO3 would decompose back into these 2 things. And you would find that you have 2 reactions taking place at the same time in the same container. So we can actually split those reactions. We can write the forward reaction, which is your SO2 and your oxygen combining to form SO3. And then there's the reverse of that would be your reverse reaction, where your 2 SO3 are uncombining to form SO2 and oxygen. So you'll find that you have both of these reactions taking place at the same time. This kind of reaction is called a reversible reaction. All right, so let's say we start with some sort of a flask or a container, and we put into it some SO2 and some O2 molecules. So we have some SO2 and some O2 molecules in the container, and no SO3, so no SO3. They are going to start to combine and form SO3 molecules. So you'll notice that in this graph here, as time goes on, you start with SO2 and O2 and no SO3, and then as they start to combine, you're going to start to form, as time goes on, SO3. But you'll also notice that you're going to start to lose SO2 and O2. And the reason why is because they're combining to form SO3. Now, of course, once you start to combine to form SO3s, those are going to start to break back down into SO2 and O2 molecules. And if you let this just take place, these 2 reactions in the flask, eventually what you're going to find is that your concentrations of SO2 and O2 are going to flatten out. And your concentration of SO3 is also going to flatten out or become consistent. And at that point, when that happens, so right around here, that's when you've reached something called chemical equilibrium. So that's where equilibrium is achieved. So chemical equilibrium is a point where your forward reaction and your reverse reaction are happening at the same rate. So if you look at this little animation, what you have are 2 ants, and they're carrying rocks from 2 different piles in 2 different directions. And this is what chemical equilibrium is like. Your reactants are becoming your products at the same rate that your products are becoming your reactants. And you never get a gain on either side. So as the reactants are breaking down into your products are breaking or turning back into your reactants. and you don't get a gain on either side. This is chemical equilibrium. So you've got a balance. You don't get a gain of reactants or a loss of reactants. You don't get a gain of products or a loss of products. The other thing that chemical equilibrium is it's dynamic. Dynamic just means that it never stops, that both reactions, if you leave it alone in a closed environment, they'll just keep going forever. So it's not like they go until they get to a certain point and then stop. They just keep going, just like these two ants. It's important that you understand that what chemical equilibrium is not is that the concentration of your reactants is equal to the concentration of your products. And that's what this picture is supposed to show you, is that no matter how much reactant and how much product you have, notice they're not equal piles. So just because you have a big pile of reactants and a little pile of products doesn't mean that at chemical equilibrium, those will become equal to each other. As long as the rate of these forward and reverse reactions stays the same, it doesn't matter if the two piles are the same size. Chemical equilibrium doesn't mean that you have the same amount of reactants as you do products. From a balanced chemical equation, you should be able to express something called an equilibrium expression. And so my example again is this SO2 and O2 equation. Once at equilibrium, where the forward and the reverse reactions are equal to each other, I can write this expression right here. This is called an equilibrium expression. So let's talk about what the parts are. Keq. That's called an equilibrium constant. And at some point, we're actually going to plug a number in for this, but for now, I just need you to be able to write that Keq is an equilibrium constant. It's for a particular reaction, so in this case, this particular reaction. And we can set that equal to this phrase or this mathematical ratio. On the top, we're going to put SO3, which is on the product side. So we're going to go ahead and call this the right side of the reaction because, with chemical equilibrium, there really isn't products and reactants anymore since you have two reactions taking place. But as it's written, it's the stuff that's on the right side. So we'll call these your products, even though I realize that, that can be tricky. In brackets, and then raised to the stoichiometric coefficient. And then over that, we're going to write SO2, the reactants, in brackets, raised to the stoichiometric coefficient 2. And of course, oxygen in brackets. And then raised to the power of 1 just means you don't have to put anything there. So what are the brackets for? Well, the brackets represent the molar concentration of whatever that substance is. So you would read this, the molar concentration or molarity of SO3, and then of course you're squaring it, over or divided by the molar concentration of SO2 squared, because it's got a 2 in front of it in the balanced equation, multiplied by the molar concentration of oxygen. So this is called an equilibrium expression. And at some point, we're going to actually plug numbers into this and solve for some of these parts. All right, so when you're writing an equilibrium expression for a reaction, there are a couple of rules. So again, the first rule is that your reactants or your products, whatever's on the right side of the equation, you're going to put on the top of your ratio. And the reactants, whatever's on the left side, will go on the bottom. Make sure you put them in brackets and you raise them to their stoichiometric coefficients. The second rule is that anything that's a solid or a liquid, so you got to pay attention to these little subscripts here. If there's ever an S or an L, you do not put them into the equilibrium expression. And there's a reason why. Solids and liquids don't have concentrations. If you think about that, it actually makes sense. If I have pure water, it doesn't have a molar concentration because there's no moles of solute over liters of solution because it's just all water. So it doesn't actually have a molar concentration. Neither does a pure solid. A pure solid is just that. It's all one thing. So it doesn't have a molar concentration. Now, gases can have a molar concentration because they actually respond to changes in volume. So gases and things that are aqueous will actually go into the equilibrium expression. It's only things that are solid and liquid that you leave out of the expression. And in this equation, everything was a gas, so it all goes in. So let's do another one. Here's a chemical reaction. I want you to pause this and write the equilibrium expression, and then unpause and see how you did. Okay, so here's the answer. Your CO2 raised to the power of 2 in brackets on the top, and your CO raised to the power of 2 in brackets on the bottom. These are the only two things that go in the equation because both tin oxide and tin are solids, and they wouldn't go into our equilibrium expression. All right, so let's talk about this Keq value, and now that you know how to write an equilibrium expression, we're going to actually calculate some Keq values. So Keq, you'll remember, stands for equilibrium constant. And it's the equilibrium constant for a certain or particular reaction at a certain temperature. So the only thing that will change Keq is temperature. So when you change the temperature of the reaction system, then your Keq value is actually going to change. So you'll often see Keq values associated with temperatures. The temperature isn't involved in any calculations. It's more informational for you. So you know that that Keq value is at that particular temperature. All right, so again, you can calculate Keq from equilibrium concentrations of reactants and products. So what that means is that the only time you can calculate Keq is once the system has reached equilibrium. And at that point you will know, or you might be given, or you can test the system, and you can get concentrations of your reactants and your products. So for example, this reaction, we've got these concentrations of our product and our reactant at equilibrium. So we know equilibrium has been reached. And we're asked to calculate Keq. So the way you'll do that is the first thing you're going to do is you're going to write an equilibrium expression. Remembering that whatever your products are, go on the top in brackets, and then you square them, or rather, in this case, you'd square them because of the stoichiometric coefficient. And then your products go on the bottom in brackets, and you leave out any solids or liquids. In this case, there are no solids and liquids, so it was all gas and everything goes in. And then from there, you're just going to plug your numbers in. Don't forget that you have these stoichiometric coefficients that you raised to your concentrations to the power of. Don't forget those. So I'm just replacing the bracket NO2 with this number, and of course I'm squaring it. And then I'm replacing where it says bracket N2O4, I'm replacing all of that with 0.0045. And now this just becomes a math equation. And when I work it out, I get this number, 0.20. Notice Keq has no unit on it. So this number, what the heck does this number even mean? So we know that the equilibrium constant for this reaction is 0.20, but who cares? What does that mean? Well, that number actually tells you quite a bit about the reaction. So these values that you get for Keq actually tell you a little bit about what's going on in this system at equilibrium. So we know that at equilibrium, these two reactions are taking place at the same rate. So the N2O4 is decomposing into two NO2 molecules as fast as they are joining back together into N2O4. But that doesn't tell you what there's more of in our system. It doesn't tell you what side of the reaction there's just more reactants or products on. And that's what this number will tell you. So this number right here is less than 1. 0.20 is less than 1. And for a number, for this equilibrium expression, when you plug numbers into it, to end up with a value of less than 1, that must mean that whatever number we had on the bottom is going to be bigger than whatever total we had on the top. Because a bigger number on the bottom divided into this number would make a smaller overall value. So that tells me, because on the bottom, of course, if you remember correctly, these are your reactants and these are your products, that tells me that my reactant side is favored at equilibrium, that there's just more reactants or a higher concentration of reactants at equilibrium than there are products. All right, so what if we had worked out or calculated Keq from equilibrium concentrations and we got a Keq that was greater than 1? Well, that would mean that whatever we ended up with on the top was a greater amount than what we ended up with on the bottom. So of course you divide a small number into a larger number, and that should give you a number of greater than 1. So that tells me that my products are favored at equilibrium, or that I have more products than I do reactants at that point. And then hopefully you realize that if it's equal to 1, then that means neither side would be favored, that our reactant concentration is exactly equal to our product concentration. And finally, let's talk about what this Q thing is. So Q is similar to Keq. It's called the reaction quotient. The difference between Q and Keq is that Q is when we're not sure if we're at equilibrium, and Keq is when we know we're at equilibrium. So you calculate Q exactly like you would calculate Keq. You write an equilibrium expression, and then you plug your concentrations into it and you solve. Now, we don't call it Keq because we don't know if the system is at equilibrium. If it is at equilibrium, then our Q value should equal our Keq. If it's not at equilibrium, they won't equal the same thing. All right, let's do a quick example because I think that's the easiest way to discuss reaction quotient. So here's a reaction where you've got N2 and H2 combining to form NH3, and of course NH3 breaking back down into N2 and H2. So let's say we've put all this stuff in a flask and we walked away, and we came back and we wanted to know if we were at equilibrium. And we knew that at equilibrium we would get a Keq of 0.105. And we go in and we take readings and we find that NH3 has a concentration of 2 molar, N2 a concentration of 1 molar, and H2 a concentration of 2 molar. And we want to know if the system has reached equilibrium. So is it at equilibrium yet? The only way we're going to know that is to try to calculate Keq, but we can't call it Keq because we don't know if we're at equilibrium yet. So the first thing we're going to do is we're going to set up our equilibrium expression, but instead of equaling it to Keq, we'll equal it to Q, or we'll set it equal to Q. Because again, we don't know if we're going to get this value right here or some other value. Then we're going to plug the values that were given into our equilibrium expression, and it's going to look like this. And then we're going to do the math. And when we do that, we get 0.5. So from here, we're going to go, okay, well, does Q equal Keq? It doesn't. Those two numbers aren't the same number. So that tells me that this reaction has not reached equilibrium yet. So not only can we surmise or figure out whether or not we have reached equilibrium by calculating Q and comparing it to a known Keq value, but we can also kind of get an idea of what needs to happen or how this reaction needs to progress to get to equilibrium. So that's another thing we can get from Q. And so what does Q tell you? What does the value tell you? Well, first of all, if our Q value that we calculate is equal to our given Keq value, if those two numbers are the same, then we know that our reaction is at equilibrium and that the concentrations that we use to calculate Q are actually your equilibrium concentrations. So the reaction has reached equilibrium, and it's not that it's done, because it doesn't stop, but it's at equilibrium. Well, if your Q is greater than your Keq, so you calculate your Q and you get a number that is greater than Keq. So like here, this number is bigger than this number. What that tells me is that I have too many products in my system and not enough reactants, or rather that I'm producing more product than I am reactant. So my forward reaction is happening at a faster rate than my reverse. So to get to equilibrium, the reaction needs to, what we say is proceed to the left. That means towards the reactants to get to equilibrium. So we need to get rid of some of the product and make more reactant so we can make this total number smaller and hopefully get to Keq. The opposite, of course, would be true if our Q ended up greater than KEQ, or sorry, less than KEQ. So if we had calculated this and it had come out to be less than our KEQ value, what that tells me is that the bottom number is too big and the top number is too small. So I need to actually make the product concentrations, they need to get higher and the reactant concentrations need to get smaller so that I can raise my Q value to equal my KEQ. So that tells me that the reaction needs to proceed to the right or towards the product. So we need that forward reaction to kind of speed up and the reverse reaction to slow down to get us to equilibrium.